Okay, let's go ahead and get started. So today what I would like to do is complete our discussion of cosmology, which we began with last class, or I guess the class before last. So let me just, given that it's been a little while since our discussion of FRW cosmology, let me just remind you of a few of the basic features of our models of cosmology that we worked out last time. So we're interested in discussing the evolution and dynamics of the universe as a whole, and in doing so, we decided to adopt a simplified model known as the FRW model, which is supposed to be valid on very long distance scales, where you average out over all of the irrelevant little fluctuations like us, galaxies, stars, inhomogeneities, and so forth, and you assume that on its largest distance scales, the universe is spatially homogeneous, if you can read that, and isotropic. Homogeneous in the sense that there is no preferred point in space, and isotropic in the sense that there's no preferred vector in space. What does that mean from a practical point of view? From a practical point of view, that means that the metric that describes the universe on very long distance scales has a time component and a spatial component. And the spatial component, which I've written here as d sigma squared, can take one of three forms. It has to be a three-dimensional spatial geometry, which is homogeneous and isotropic. So the simplest homogeneous and isotropic case is the one that we refer to as k equals 0. So first let me write down the metric on the spatial slice. It's dr squared over 1 minus kr squared plus r squared d omega squared, where d omega squared is the usual metric on the two-dimensional sphere, d theta squared plus sine squared theta d phi squared. And k is either plus or minus 1 or 0. So k labels the three different types of spatially homogeneous and isotropic geometries. So for example, if k is equal to 0, then the spatial slices are flat. If k is equal to 1, then the spatial slices are the three-dimensional analogs of the sphere. And in that case, we say that the universe is closed, because a sphere has a finite size, whereas if k is equal to minus 1, the spatial slices are three-dimensional hyperboloids, and the universe is said to be open. So the dynamics of the universe, then, is described by two things. It's described by the parameter k, which is 0, 1, or minus 1, and it's described by the function a of t, which is the scale factor. That's some function of time that tells you how the size of the spatial slice evolves in time, and its dynamics is governed by Einstein's equations. So a of t is found by solving Einstein's equations, and in order to solve these equations, we need to make some assumption about the sort of matter which is present in the universe. And the Friedman model, maybe there's only one n, is a very simple and accurate assumption for the type of matter which is present, namely, which is that the matter is a perfect fluid, or more precisely, a sum of a bunch of different types of perfect fluid with some pressure rho, some energy density rho, and pressure P. So in order to understand the dynamics that govern the universe, we then need to write down the equations of motion, which are Einstein's equations. For A, so this was the spatial component of the Friedmann equations. This is the most important Friedmann equation. And there was also a time component, which was another equation that involved the second derivative of A. So this is the equation that one must solve to determine A as a function of time. And the energy density rho and pressure P are also functions of time, which by the conservation of the stress tensor will obey a first-order differential equation that I have written down here. And these two equations you will derive, or you have derived, for the first problem on the problem set, which is due tomorrow. Okay, now what I would like to do is proceed to discuss the actual dynamics of our universe as we have observed it. So in our universe, there are a bunch of different types of matter that are present. And so it's useful to, before diving into any details, just think a little bit about qualitatively how the dynamics of the universe will evolve if you have several different types of perfect fluid present. So for our universe, we have several different types of perfect fluid present. We have several different types of matter, all of which will govern the dynamics of the universe at different points in the evolution of the universe. So, for example, we have dust, we have radiation, we probably have a cosmological constant, and we may have curvature. So in order to treat all of these different sorts of matter on a unified footing, what I will do is I will define a parameter h, which is a dot over a, and then I will write the Friedmann equation, which is this equation of motion for the scale factor a, as an equation for h. So you can see that it takes the form of h squared is 8 pi g over 3, and then I need to sum up the contributions from all of the different types of matter present. So I'll write a sum over I, where I runs over all the different kinds of matter that are present, of rho I. Where here I'm thinking of curvature, so I'm thinking of this curvature term here as another sort of matter. So I could define rho sub k to be equal to minus 3k over 8 pi g times 1 over a squared. And then I could just treat curvature as another sort of matter in the sense that it appears as a source term on the right-hand side of Friedmann's equation, which governs the evolution of the scale factor a through its dependence on this Hubble parameter h. So h here is the Hubble parameter, which has units of inverse time, or inverse length, and it describes the typical time that it takes. So H inverse is the typical time it takes for the universe to expand by a power of E. So for the size of the universe to increase by a factor of E. And the important point is that because of the conservation equation that we wrote down above, these rho i's will have a dependence on time that is relatively easy to solve for. So, for example, for a fluid with equation of state, so that the pressure is linearly related to the density, then the conservation equation, which I wrote down above, so here's the conservation equation, then becomes a first-order differential equation for rho, which says that rho is going to be related to A to some power. So this is what we solved last class. And it says that rho is equal to a constant, something independent of time, times A to minus 3 times 1 plus W, where W is just that constant that tells you about the equation of state of the matter that you're considering. For example, if you have radiation with W equals to 1/3, so that's just the statement that the pressure of a gas of photons or a gas of massless particle is 1/3 the energy density of that gas of massless particles, then that tells you that rho will go like A to the minus 4. So that at very early times, the energy density of a gas of photons or of massless particles will be very large, but then it will very quickly redshift with the fourth power of the size of the universe. Whereas if you have dust, so that W is equal to 0, that's just to say that dust is a pressureless fluid. So for example, by dust here we could mean stars, galaxies, us, anything which does not have pressure. Then rho goes like A to the minus 3, whereas curvature, as we have defined it, redshifted like A to the minus 2. So if you thought of it as a perfect fluid, it would have energy density, equation of state parameter, minus 1/3. And vacuum energy, or cosmological constant, has W equals minus 1, so that the energy density does not redshift at all. So then, comparing this to the equation for the Hubble parameter H, which was A dot over A, which was 8 pi G over 3, sum over I, rho I, you can then read off from this, at least qualitatively, the history of the universe. So what this says is that as the universe expands, at very early times, when A was very small, when the size of the universe was very small, the expansion of the universe was governed by radiation. It was governed by photons and whatever particle physics analogs of photons we have that drove the expansion of the universe at early times. Then at later times, those photons, those other particles, the gas of which drove the expansion of the universe, have their energy redshifted away very quickly, and the expansion is then driven by dust, or what we would also call normal matter, like stars, galaxies, and so forth. And then at later times, the other more relativistic forms of matter, such as curvature and vacuum energy, will take over. So this then is a caricature of the history of the universe. And what I would like to do today is go a bit beyond this caricature and tell you about the actual history of the universe and discover the ways in which that caricature, it actually turns out, is not at all true. So this caricature of the different phases dominating at different times is sort of a very simple model of cosmology, which one might have learned if one took a class on cosmology 20 or 30 years ago. But in fact, recent observations have allowed us to nail down with a really great degree of precision the various types and densities of matter that are present in the universe. And so we can in fact see that this caricature that I presented to you last class is in fact not entirely true. And there are still a few surprises that remain in the study of cosmology. So this was just a sort of brief review of what we did last class, just because it was a little time ago. Maybe I should pause here and see if there are any questions before I dive into the new material. Any questions? Speak now or hold your peace forever until the heat death of the universe. Well, as we'll see, the heat death isn't really the thing that you should be worried about. Okay, we'll get back to that. Yeah, this is good stuff. Okay. So before diving into a discussion of the observations and what they tell us about the evolution of the universe, what I would like to do is just complete our discussion a little bit by asking, what does the universe look like during a period during the evolution of the universe when one phase or type of matter dominates. So, in general, the differential equation that we will have to solve will have on its right-hand side a sum of these four different terms, which are proportional to a to the minus fourth, minus third, minus second, and a0. So that differential equation can't be solved explicitly. Of course, it can only be solved numerically. But if we're working in an epoch where we can ignore all but one of the terms that appear on the right-hand side of that equation, then in fact it's very easy to write down the solution to the differential equation. So let's say that we have a matter density which goes like a to the minus 3, 1 plus w. Then, and we can ignore all of the other terms on the right-hand side. Then the equation a dot over a squared is equal to a constant times a to the minus 3, 1 plus w is such a simple equation that even I can solve it. So why don't I go ahead and attempt to do so, even though I haven't finished having my coffee. So let's just rearrange that a little bit. What does it say? It says that this constant is equal to a dot squared times a to the 3, 1 plus w minus 2, or the square root of this constant is a dot times 3 halves 1 plus w minus 1, or a dot times a to the 3w over 2 plus 1 half. And let's stare at the right-hand side of this equation. What is that? That is just the time derivative of a to the 3w over 2 plus 3 halves times some constant out front. And I'm not being very careful about the constants. What is that constant? That's 1 over 3 times w plus 1 over 2. So what this says is that a to the 3 w plus 1 over 2 is equal to some constant. Okay, this is now a different constant from the one I wrote above, times t minus t naught, where t is the time variable and t naught is some constant of integration. Or a is a constant times t minus t naught to the 2 over 3 times w plus 1 power. So that the metric ds squared is minus dt squared plus a squared times d sigma squared. So that's t to the 4 over 3 w plus 1 d sigma squared. And you can see now why I haven't been terribly careful about keeping track of that constant out front. It'll be important if we're doing the details, but we could always get rid of it by a change of coordinates, reabsorb it into t or sigma. So this is what the evolution of the universe will look like if we happen to be in an epoch where we can ignore, to a great degree of precision, all but one of the terms that will drive the expansion of the universe. So this metric has a name. It's a rather boring name. This is called an FRW universe with polynomial expansion. Why polynomial? Well, it's t to some power. Okay. Not very creative. By the way, I've shifted my t coordinate to get rid of t naught. Hopefully that's clear. I could write t minus t naught to the 4 over 3w plus 1 power here. So you can see that as the equation of state parameter increases, the expansion will be slower. If w is very large, such as for radiation, then it'll be t to some rather small power as compared to larger powers if the equation of state parameter is less. So radiation will make the universe expand less than will dust, which in turn will make the universe expand less than will curvature, and that in turn will make the universe expand much less than a cosmological constant. So there are probably two special cases that I should comment on here. So let me first consider the case where we just have a curvature-dominated universe. So what would the universe look like if we only have a curvature term that acts as a source in the equations of motion? So that would mean that w is equal to minus 1/3, and a will go like t squared. And in fact, what I would like to do is bring your attention to this equation that I wrote up here. Here it is. Okay. So if we're ignoring all of the other terms that will appear right here, and only keeping into account curvature, then and remember the parameter k has to be 0, 1, or minus 1, then because the left-hand side of this equation is positive, the right-hand side must be positive as well. So k will have to be equal to minus 1. So in order to have a curvature-dominated phase of the universe, we must have k is equal to minus 1. And what does the universe look like in that case? Well, it's minus dt squared plus t squared times the metric on the three-dimensional hyperboloid. So let's think about what that geometry is for a second. It's a geometry whose spatial slices are hyperbolas, and it's a solution to Einstein's equations if you have no matter whatsoever. Because what was curvature? Curvature was just an effective contribution to the equations of motion that looked like it came from matter, but it actually came from the spatial curvature of the spatial slices of space-time itself. Okay, that's what the geometry looks like. In fact, I claim that you know this geometry very well, and you've spent a large portion of your lives studying it. Can anyone guess for me what this geometry is? I've given you all of the information you need to guess what this geometry is. I'll give you a hint. It's the solution of Einstein's equations without any matter present. And it has lots of symmetry. This is Minkowski space. But it's Minkowski space written in funny coordinates. Let's think about this for a minute. So this space apparently has a singularity at t equals 0. This is what you might call the Big Bang singularity of this cosmology. However, you know plenty of examples where you take Minkowski space and you write it in a funny coordinate system where it looks like it has a singularity. For example, in three-dimensional flat space, you're used to writing down coordinates dr squared plus r squared times d omega squared, where d omega squared is the metric on the sphere. And that r equals 0 point looked like a singularity, but in fact, nothing special was happening there. Your coordinate system was just breaking down. This is the time-like version of that geometry. It's the metric on flat space where the dr squared plus r squared times the metric on the sphere has turned into minus dt squared plus t squared times the metric on the hyperboloid. So r has been replaced by t, and the sphere has been replaced by the hyperboloid. But in fact, this is a very simple space-time. It's just Minkowski space written in what are known as Milne coordinates. So I bring this up just as a lesson that sometimes cosmologies can look very complicated. You know, this has got some complicated time dependence in the metric. It's got some complicated hyperbolic spatial slices. But in fact, there's nothing fancy going on here. It's just Minkowski space written in some silly coordinates. Okay, there's another special case that I would like to bring up, which is the case that I was ignoring when I derived this form up above, which is the case where this metric breaks down, namely when W is equal to minus 1. So if W is equal to minus 1, clearly something very strange is happening to the dynamics. So let me remind you that W equals minus 1 was the case when the dynamics was dominated not by radiation, dust, or curvature, but rather by vacuum energy, or by a cosmological constant, which has W equals to minus 1. In that case, rho was just a constant because the energy density of vacuum energy does not redshift away at all with respect to time. So A dot over A, which was H, was just a constant. And in this case, the metric does not expand in a polynomial manner with T, but instead it expands exponentially. So A goes like e to the ht, and the metric is minus dt squared plus e to the 2 ht times d sigma squared. Now, in the limit where we're neglecting the curvature term that appears on the other side of this equation, then this d sigma squared should just be flat space. And so, for example, the metric minus dt squared plus e to the 2 ht times the metric on flat space, flat three-dimensional space, is in fact the metric that we have also encountered before in this class. It is known as de Sitter space. So you can see that if you have a cosmological constant dominating the evolution of the universe, then the expansion of the universe with respect to time is exponential rather than polynomial. And because of that, the qualitative dynamics of the universe governed by a cosmological constant or by vacuum energy is qualitatively different than if it's governed by some other sort of energy. And so if there is a vacuum energy present in the dynamics of the universe, that has a very profound effect on the late-time behavior of our universe. It means that space will end up expanding exponentially at late times rather than in a power law way. And this, in fact, is a very interesting question then as to whether or not there is vacuum energy or there is a cosmological constant. Because if there is, and if it governs the dynamics of the universe at late times, then that means that there's some qualitatively surprising behavior of our universe in the far future, which we'll discuss in a minute. Well, in fact, we could discuss it right now. What does it mean if the universe is governed by vacuum energy? Well, if the dynamics of the universe is governed by vacuum energy, then it is the ultimate existential nightmare. Why is it the ultimate existential nightmare? Well, it's the ultimate existential nightmare because if you are all sitting at points of constant x in this classroom, listening to me give a lecture at a point with different constant x, sitting here at the front of the classroom, then that means that at very late times, you and I will be receding away from one another at speeds that grow exponentially in time, and eventually will exceed the speed of light. So that means that you, sitting 3 feet away from me, will be receding from me at such a great speed that eventually we will be out of causal contact. Eventually there will be a horizon, just like the event horizon of a black hole, which will separate any two time-like geodesic observers. So any two time-like geodesic observers will generically, unless they happen to be sitting at exactly the same point at late times, be separated by a horizon. And thus they will be out of causal contact. So what is the Sartre play? Hell is being stuck in a room forever with your friends. This is like that, except the opposite. For example, if the dynamics of the universe is governed by a cosmological constant, then 100 billion years from now, all of the galaxies that we see in the sky will eventually start receding away from us, not with a velocity that is constant in time, but rather with a velocity which accelerates. And so they will gradually become redshifted and redshifted and redshifted by the evolution of the scale factor until eventually they all become invisible. So eventually, all of the galaxies that we see in the sky will gradually fade from view as they become redder and redder and redder and pass behind our horizon. And then, at very late times, the dynamics gets very interesting because you either have two possibilities. Either you can bind together gravitationally with some object and stay in causal contact, or if you're following geodesics in the de Sitter universe, you'll recede from one another and fall out of causal contact. Yes?
When will that happen?
When I discuss, yes?
The equation, when will that happen?
So you can see here that H here is a parameter that has dimensions of inverse time. So the typical expansion scale, so the typical time scale for an exponential expansion of the universe will be H inverse. Okay. The universe expands by a factor of E once per time H inverse. So I'll get down, when I tell you about the actual observed values of these constants for our universe, then we'll discuss what sort of numbers would go here. If you want a number to keep in mind, H inverse is about 10 billion years. It's about the age of the universe. So we're talking, this stuff will happen, 100 billion, trillion years from now. I mean, I wouldn't get too exercised about it at this instant. It does keep me awake at night, however. Okay. Without any further ado, then, I would like to tell you the answer to the question, then, what does our universe look like? So, before discussing the dynamics of the universe at early times, let me just tell you about the dynamics today. So, today, radiation is a negligible contribution to the energy density of the universe. And so the dynamics today is governed only by matter, by which I mean normal matter, that is to say dust, curvature, and vacuum energy. And so it's typical when cosmologists discuss the dynamics of our universe today not to use the parameters rho matter, rho curvature, and rho vacuum energy, but instead they redefine them by a factor of h squared. So people define a number that we call omega matter, which is 8 pi g rho matter over h squared, Remember that the equation says that h squared is 8 pi g times rho matter plus rho curvature plus rho vacuum energy. So here I'm just dividing by a factor of h squared in defining my parameter omega. Likewise, omega of curvature is minus k over h squared a squared. And omega of vacuum energy, or cosmological constant lambda, is 8 pi g, I guess there was a 3 here, over 3 h squared times rho lambda. So that the Friedmann equation, which says that h squared is 8 pi g over 3 times rho matter plus rho curvature plus rho lambda, says that omega matter plus omega curvature plus omega lambda is equal to 1. And I just remind you that this guy here will redshift like a to the minus 3. This guy here will redshift like a to the minus 2. And this guy here will not redshift at all. Now, over the last 10 years or so, 15 years or so, there's been a real revolution in our understanding of precision cosmology. So we've been able to nail down these parameters for the universe today within a factor of a couple percent. So there are a variety of different ways that these parameters have been studied, and they all give more or less the same answer. I'm not going to try and be terribly precise about how these observations are done, but the answers within a factor of a couple percent are the following. Omega curvature is 0. Omega matter is about 0.25, and omega lambda is about 0.75. So, there are two very surprising things about this answer. The first very surprising thing is that one of these parameters happens to be 0. Okay. Omega curvature is approximately 0, so that the universe is roughly flat. The other surprising thing about this equation is that two of them are actually roughly the same size. If you think about it, omega matter, omega curvature, and omega lambda all have very different behaviors as a function of A, and in particular have very different behaviors as a function of time. So, generically, you would expect that one of these would be much larger than the other two. But in fact, you can see that within a factor of 3, omega matter is of order omega lambda. And so that means that we happen to be living in a very special time period in the evolution of the universe. It's a time period where there's not a single type of matter that's dominating the evolution of the universe, but rather a combination of two types of matter. So the current dynamics of the universe is governed both by vacuum energy and by matter. So sometimes people give a special name to this remarkable fact. They call this the why now problem. Of all the various different times that we could be here to be measuring the various cosmological constants, why does it happen to be that we are measuring these constants at a time when two of them are of order the same magnitude? Yes?
Is the coincidence that this looks the same as the dispersion of matter in the universe, 25% matter, 75% dark energy?
No, that's precisely this is precisely the statement. This is the statement that the current dynamics of the universe appears to be governed by 25% matter and 75% dark energy.
So if there was more curvature energy, then the one would be lower?
Absolutely. the equations that govern the dynamics of the universe, Einstein's equations, say that the three of them sum up to 1. Okay? And if I've done everything correctly, then 0.25 plus 0.75 will indeed sum up to 1. I won't bother to check that right now. That's a joke. Any other questions? Okay. So this data allows us to understand the future of the universe, the future evolution of the scale factor A of t. So the way that people typically describe this is they typically draw a plane whose two axes are given by omega lambda and omega matter. And then if I specify a point on this plane, namely I specify omega lambda and omega matter, then I can read off from that omega curvature. Omega curvature was 1 minus omega lambda plus omega matter. So a line of constant omega curvature is a 45-degree line. So for example, here I've drawn the line where omega curvature is equal to 0. And if you're on this side of the line, then omega curvature is positive, and we have an open universe. And if you're on this side of the line, omega curvature is negative, and you have a closed universe. So depending on where we live on this chart, the universe will either be open or closed. And as we saw earlier, the late time dynamics is going to be governed by the cosmological constant, or the value of omega lambda. And if omega lambda is positive, then the universe will expand forever. And if it's negative, then the universe will want to collapse. So up here, the universe will want to expand forever. And down here, the universe will want to collapse. And that depends on whether omega lambda is bigger or less than 0. Okay, there's a slight subtlety here, which is that if omega lambda is rather close to 0 and omega matter is very large, then it might be that the universe will never expand to a sufficient size that omega lambda will take over the expansion of the universe. And instead, the matter will just cause everything to collapse. So because of that, if you actually do this precisely, there's a little curve upward down here at the end. Yes?
Our universe could be open and still collapse?
Absolutely.
How does that work?
If the universe is open and it collapses, so if the universe if the cosmological constant were negative, so when I wrote down my equation for the evolution of the scale factor with a cosmological constant, I, with the malice of forethought, had taken the cosmological constant to be positive. But if the cosmological constant were negative, you have a geometry which is known not as de Sitter space, but anti-de Sitter space, and in that case, the universe will want to collapse. However, we are fortunate or unfortunate enough to live in a universe where that does not happen. And in fact, if you look at where we live, it appears to be right there. So the universe appears to be very close to flat. Most of the energy density is in the cosmological constant or in vacuum energy, and a smaller fraction of that is in normal matter. So it appears that the universe today has flat slices and will expand forever. I should mention, however, that there were certain... yes, question.
When you draw a circle there, does that mean that we don't know if it's open or closed?
That's right. So there's some of order a few percent error in these determination of these. There's some uncertainty in the determination of these constants. You know, we observe omega matter, it's about 0.25. We observe omega lambda, it's about 0.75. We determine omega curvature by adding the two of them and seeing if they're equal to 1 or not. You know, there's some...
How is it determined by adding those two?
Yeah, that's right. So there's some uncertainty observationally within a few percent. So it may be that the universe, spatial slices are not exactly flat, but rather they have some curvature which was of order 1 a long time ago, and it has redshifted away. Okay. The confusing thing would be, why would it redshift away when the matter has not redshifted away? Because matter redshifts away more quickly than curvature. That's one way of stating the why now problem. So it looks like the universe is most likely flat. And indeed, some people will appeal to models of the very early universe, such as inflation, to give an explanation for why the spatial slices are flat. I'll get to inflation in a minute. I should mention, however, that my statements about the future of the universe have relied on a very particular assumption. They relied on the assumption that the matter density present was a perfect fluid with this P equals W rho equation of state. So we're not entirely confident that that is the correct model for the matter density in the universe. And so I should emphasize that we're not entirely sure that the current expansion is due to a cosmological constant or vacuum energy as opposed to something else which looks like vacuum energy right now, but might look very different in the future. So there's, for example, a model known as quintessence, which is a model for a sort of matter which will derive the dynamics of the universe for a while that looks like a cosmological constant, but then will stop looking like a cosmological constant. So omega lambda is therefore sometimes referred to not as vacuum energy, which describes a particular assumption about the relation between the pressure and the energy of this matter. Instead, it's sometimes referred to as dark energy. Energy, because it's a little similar to vacuum energy, it appears to have no pressure, at least, or it appears to have P equals minus rho, at least right now. And dark, because we can't see it. Okay. We only see it through its effect on other objects. You know, the story of the observation of omega lambda is a really fascinating story in the history of physics. You know, when I was an undergraduate and I was learning about cosmology, everyone taught me that omega lambda was equal to 0. Why did they tell me that omega lambda was equal to 0? Well, it hadn't been observed, and people naturally thought that if omega lambda was non-zero, then it would be absolutely gigantic for quantum mechanical reasons. And people assume that, well, if it's not observed, then it must be 0. However, it was only around 1997 or 1998 that some observations began trickling in from supernova data that hinted that omega lambda was non-zero. This was initially quite controversial. It was the first observation that the universe is not only expanding, but it is expanding at an accelerated rate. So this required some heroic observations of supernovas, as well as a great deal of understanding about the details of supernovas in order to calibrate the luminosity measurements of these supernovas appropriately. And since then, it has been verified using several other techniques. So, for example, the cosmic microwave background also provides an excellent window on the current and early dynamics of the universe and has verified to a great degree of accuracy these earlier experiments. So I think at this point, it's not particularly controversial to say that omega lambda is not zero. But if you'd taken this class 10 or 15 years ago, the story probably would have been quite different. So I think it's a very exciting time to be thinking about these issues because it's a story which has changed quite dramatically in the last decade or so. A second mystery, and something that you may have also heard about, is that omega matter, as we measure using these supernova and other sorts of observations, is about 0.25. But if you take the matter density of all of the stuff that we can see, such as stars, galaxies, etc., then that's only about 0.05. So if you take all of the stuff that you can see, matter that gives off light, and you add up its energy density according to the best physics that we know, you only account for about a fifth of the matter density that is necessary to explain the observed evolution of the universe. And so we give a name to the other matter which must be present in order to drive the dynamics of the universe, but we cannot see. We call it dark matter. Between dark energy and dark matter, there's about 95% of the content of the universe out there, as measured in terms of energy density, that we can't see. But that we know is there because we have observed it indirectly by measuring the evolution of the universe. I think the explanation of these two dark forms of matter is going to be a very exciting thing to work on over the next few decades. I think the smart money is probably on dark matter being a gas of new elementary particle, which may or may not be observed at the Large Hadron Collider. I think that's not entirely clear, but I think there's a good chance that we'll discover in the next few years a new particle which might account for dark energy. So there are a variety of indirect indications that this might be the case, so I recommend that you stay tuned. Okay, so let me just give you a few numbers to keep in mind when thinking about cosmology. So the Hubble parameter today is around 70 kilometers per second per megaparsec. Okay, that's not the most fundamental choice of units that I could use, but it's a good one for thinking about astrophysics. Means that if you have something that's a few million light years away, then it's receding from you at a speed of roughly 70 kilometers per second. For cosmological reasons. People sometimes refer to h not as the Hubble parameter, but as the Hubble constant. That's unfortunate because, as you have learned, it is not a constant unless you are in de Sitter space. But people sometimes use that phrase. If I were to just rewrite this using different units, h inverse is around 10 billion years, or 10 to the 17 seconds. That's roughly the age of the universe. I think if you put in the numbers, go through it in detail, then you end up with something like 14 or 15 billion years between now and the early phase of the universe when light could no longer propagate, as we'll discuss in a second. Yes, question.
Is that meaningful?
H inverse is a parameter that has units of time.
Yeah.
So 10 billion years is roughly the time it takes for the universe to expand by some finite factor of, E.
Is it meaningful that H inverse is approximately the age of the universe?
Yes, it's why, So if you go through the details, of course, in order to determine the age of the universe, you need to add up all of the matter that's present and evolve backwards in time and see when the universe began. If you just want to do a rough back of the envelope, then you say, well, look at H today, and, you know, order of magnitude, it's the age of the universe. You know, it's just good to keep these numbers in mind when thinking about the rough time and length scales associated with our universe. And so, for example, if I were to write this in dimensions of length rather than time, then I would find the rough size of the universe, which is about 10 to the 28 centimeters. So I have spent the last few minutes discussing the universe today and how the universe will evolve in the future towards a geometry which is possibly, but not certainly, going to expand exponentially forever. I would like to spend the last little bit of time in our lecture today discussing the dynamics of the early universe. Before I do so, however, let me pause and see if there are any other questions. Yes?
How much of the dark matter concept can be attributed simply to non-luminescent ordinary matter?
Not very much, as far as we understand, which is not particularly far. No, it's reasonably far. You would have to ask an observational cosmologist or an astrophysicist for the details, but my understanding is that there's a certain finite fraction, of course, of the matter which will come from things like brown dwarfs, which we can't see very well, hydrogen gas clouds, which aren't hot enough to radiate light that we can see, stuff like that. There is a model for, there are sort of two competing models for dark matter, roughly known as WIMPs and MACHOs. MACHO stands for Massive Compact Halo Object, which means brown dwarf, planet, gas giant, stuff like that. That was a popular model for a while. I think it's now, because of more detailed observations, fallen out of favor. And the WIMP model is now in ascendance. WIMP stands for Weakly Interacting Massive Particle, which means a gas of new particle, which is weakly interacting. So weak here refers to the weak nuclear force. So the same force that governs the dynamics of nuclei and radioactive decay. Massive means that it's more massive than the current particles that you will find in the particle data book. And there are some indirect indications, which I will allude to in a bit when I discuss the early universe, which seem to indicate that the appropriate mass of this particle is such that it could be discovered by the LHC. So massive here means mass of order TeV scale, which is the energy scale that we probe at the Large Hadron Collider. So I think there are some indications, but no sort of proof, that the WIMP model is correct and that we might discover this particle not by observing it astrophysically, but by creating it in the laboratory.
If it's so massive, why wouldn't it decay?
That's an excellent question. The point is that in order to get this model to work, you need to have a model with a massive particle that does not decay very easily. Okay. Part of the reason why it might not decay is that it is weakly interacting. That's the WI in WIMP, which would mean that it's very hard. You know, there could be a gas of these particles. We could be surrounded by a bath of these particles right now that we wouldn't detect because they don't interact very well with normal matter. Neutrinos, for example, are a great example of particles like that. I think if you wanted to build a lead wall in order to stop neutrinos, if I shoot a beam of neutrinos at you, in order for 50% of the neutrinos to stop, you need something like a light year of lead. So, you know, they're very, very hard to detect. And actually some finite fraction of the matter density comes from neutrinos. because there's tons of them. They're just very hard to detect. So there could be another species of particle with some of those qualitative features that would describe the dark matter density. So, people come up with various sorts of particle physics models which might explain why you have particles that are so massive, but at the same time that don't very easily decay into other particles. Usually if you have a massive particle, it will want to decay. Okay, but only if its interactions are such that it can't decay, then you're in business. So, in supersymmetry, for example, one of the reasons why supersymmetry is sometimes interesting is that in any theory of supersymmetry, there's always a particle with these properties. But let's not get into that in too much detail. Good question, though. Other questions? Okay. So let's talk a bit about the early universe. So at late times, or today, as I say, we now live in late times. During the early universe, other forms of matter dominated. So in particular, as we look backwards in time, not only did the universe get smaller, but it also got hotter and more dense. So at early times, the universe was hotter than it currently is and denser. Why denser? Well, you've just got a lot of matter that's packed into the same volume, you've got the same amount of matter which is packed into a smaller volume, and hotter because, well, if you pack a bunch of matter into a small volume, then it will be hot, its temperature will rise, and also the current observed temperature of the universe will need to be blue shifted as you go backwards in time, and so it will increase to some rather high values. And so, in the very early universe, the dynamics was governed by matter, which had the equation of state of radiation. And in order to determine the dynamics of the universe at very early times, you need to appeal to particle physics. And you need to see what sort of particles there are in our fundamental theory of matter, which could govern the dynamics of the universe at early times. And in fact, as the universe evolved and cooled down, various sorts of matter, and in particular fundamental particles, dominated the expansion. So, in order then to give you a brief history of the early universe, I need to give you a brief tutorial in the sorts of particles that are present. So, the most fundamental constituents of matter, as we understand them, are quarks, along with the various other sorts of particles, such as gluons. These are the constituents of the basic nuclei of matter. And if you take matter that is at extremely high density or extremely high temperature, then the various nuclei, protons and neutrons that make up the fundamental particles of matter will in fact decompose into their constituent parts, which will all run around in some sort of soup or plasma, which is known as the quark-gluon plasma. So, for example, this is the same plasma that if you go to the Brookhaven accelerator called RIC, they're creating right now by colliding gold nuclei together. And it's the same sort of matter that governed the dynamics of the universe at extremely early times. Now, as the universe expanded and the temperature dropped, these quarks and gluons bound together. So quarks bound together in order to form the usual nuclei that we see around us, protons, neutrons, and so forth. And so after the universe cooled a little bit, you have a gas of nucleons rather than a gas of quarks. And then as the universe cooled further, the various nuclei would form into atoms. So the various neutrons would decay into protons and electrons, and then these protons and electrons and neutrons would form together to form atoms and molecules of the sort that we are familiar with today. So there are two different sorts of phase transitions that the universe underwent at early times. The first was known as the confinement phase transition, because quark confinement is the particle physics name for the binding together of quarks into protons and neutrons, and the second of which is known as recombination. Where the nuclei form atoms. And this phase, where the universe was dominated by nuclear matter, is known as the Big Bang phase, or the Big Bang nucleosynthesis phase. Now, if you looked out into a telescope, and you had a very powerful telescope, so that you could look very at large distances, and in particular look very far back in time, then you would eventually see this soup of charged particles. However, it's important to understand that whereas atoms are all objects that do not carry a global charge, so an atom has the same number of, did something unplug? An atom has the same number of protons as electrons, so it has no global charge. But nuclei do. So what that means is that photons could not propagate through the nuclear matter phase. So photons could not propagate long distances before recombination. So during the phases before recombination, the universe was not transparent. The universe was opaque to light before recombination. So if you look in your telescope or your radio telescope at the light that was emitted in the very early universe, all you will ever see is this surface where recombination occurred, which is sometimes referred to as the last scattering surface. And this is the surface that is probed by all of the various cosmic microwave background experiments. So in astronomy, or at least in astronomy which uses electromagnetism, that is to say photons, we can never see directly anything that happened before recombination. We only have indirect evidence for it through the observation of this last scattering surface and through our knowledge of the theories of particle physics. In fact, I think it's a fascinating little story because even though we cannot observe directly the quark-gluon plasma or the Big Bang nucleosynthesis phase, we in fact have a great deal of indirect knowledge about these phases, in particular through our knowledge of the laws of particle physics. So, for example, through our knowledge of the laws of nuclear physics, we can understand to a great deal of accuracy the properties of the nuclear fluid, the nuclear matter, that made up the phase before recombination. And by studying the properties of this nuclear matter, we can understand, for example, the relative abundance of elements of the periodic table that were created during the recombination phase. So, the theory of Big Bang nucleosynthesis allows us to understand the elemental abundances, namely the amount of matter of different type, hydrogen, helium, lithium, and so forth, that were created during this soup of nuclear matter before the universe was transparent. And I think it's sort of fascinating that, in fact, the astronomical observations of elemental abundances is one of the most detailed checks of our theories of nuclear matter. So, the theory of Big Bang nucleosynthesis, which is based on our understanding of nuclear physics, has allowed us to predict the relative abundances of hydrogen, helium, and so forth for the early stars to a great degree of accuracy, which has been checked to the percent level. And, checks of nuclear physics are sometimes very hard to come by. And Big Bang nucleosynthesis provides the observation of elemental abundances provides a really powerful check of our theories of particle physics. So I think this is one of those beautiful times in physics when you have an interplay between our theories of the very large, general relativity, cosmology, and so forth, and our theories of the very small, the theories of the dynamics of nuclei. Are there any questions? Indeed, one of the big constraints, if you go to some particle physicist and you try and propose your new theory of particle physics, one of the biggest and most stringent constraints that you will always be confronted with any new theory of particle physics is that you can't mess up Big Bang nucleosynthesis. For example, if there was an extra species of neutrino, we have 3 generations of fundamental particles. If you had a 4th generation of fundamental particles, then that actually would mess up Big Bang nucleosynthesis. So cosmological observations, astronomical observations, place real, and in some cases, the best constraints on our theories of particle physics. It's a very beautiful story. Are there any questions? If there are no questions, I would like to spend the last few minutes of our discussion of cosmology describing a conjectured theory which is conjectured to describe the dynamics of the early universe at times well before those which I have just discussed, namely times that are when the universe was much, much smaller than those relevant for the quark-gluon plasma, Big Bang nucleosynthesis, and so forth. And this is what is known as the theory of inflation. So, before describing to you the theory of inflation, let me first describe to you the problem that inflation is intended to solve. So, the problem that inflation is intended to solve is what is known as the horizon problem. Or rather, this is the major problem that inflation solves. It also addresses some other problems. But the basic idea of the horizon problem is the following. In the standard cosmological model, the standard Big Bang model, which is the one that I have presented to you, we currently see in the sky and in particular in the cosmic microwave background, regions of the universe which were never in causal contact. So, for example, if you look up in the sky, so this is a picture of the night sky. It's not a very good one, but this is a picture of the night sky, for example, as probed by the WMAP satellite or something like that. Then you could look at a little patch of the sky over here and compare it to a little patch over the sky over here. And in fact, if you just use the standard Big Bang model of the evolution of the universe, then these different patches of the sky come from parts of space-time which have never been in causal contact, and in particular have never been in causal contact long enough for them to come into thermal equilibrium with one another. So I told you that at very early times the universe was very hot, meaning that it had a very high temperature. So you would think that would mean that all of the different parts of the universe would be in thermal equilibrium with one another. But in fact, that's not quite true. Because if I have two parts of the universe which are very far separated, and in particular are not in causal contact with one another, then the basic principles of physics say that they should not be in thermal equilibrium with another. So what that means is that these two regions should not be in thermal equilibrium. But if you actually go and observe the correlations between the fluctuations in the cosmic microwave background in the night sky, we observe that they look like they're in thermal equilibrium with one another. So in particular, if they're not in thermal equilibrium, you expect very little correlation between these two different regions of the night sky. But in fact, the night sky appears to be very, very homogeneous. So you would expect the cosmic microwave background to fluctuate by order 1 on length scales associated with this causality bound. But in fact, the correlations in the cosmic microwave background are extremely tiny. So for example, if you calculate the variation in the amount of matter density in the cosmic microwave background over the entire sky, then you would expect this to be order 1 for regions that are not in causal contact. But in fact, it's about 10 to the minus 5. So this means that it appears that these regions should have been in causal contact. And the proposed resolution to this problem is known as inflation. And inflation is the statement that at very early times, namely pre-Big Bang nucleosynthesis, the universe expanded exponentially. So rather than expanding in a power law manner, as one would expect for a gas of fundamental particles like quarks, gluons, and so forth, instead the universe expanded exponentially, which means that part of the night sky that we might think have always been far apart from one another, in fact were very near one another, because they're far away from each other right now only because the universe had expanded exponentially. And in order to explain the current values of the cosmic microwave background, in fact, this exponential phase of expansion must have been an exponential phase that corresponded to a volume of the universe that expanded by a factor of roughly e to the 60. Okay. 10 to the 30, something like that. And the observed value of delta rho over rho, the variations in the cosmic microwave background, is due to quantum fluctuations during this expanding phase. And in fact, these fluctuations in the matter density are not only during this exponentially expanding phase, are not only those responsible for the variations in the cosmic microwave background, but they're those that are responsible for the formation of all structure in the universe. So these quantum fluctuations are responsible for all the structure in the universe. Namely, in the theory of inflation, the universe will be very homogeneous, and all of the inhomogeneities that we are ignoring in our FRW model come from quantum fluctuations during this exponentially expanding phase. And these inhomogeneities are the sources, the seeds for the inhomogeneities that we observe in the universe today. So there were inhomogeneities produced by quantum fluctuations during the early universe, which gradually grew as the universe expanded. These inhomogeneities led to parts of the universe where there was more matter than some other parts of the universe, so that matter would clump, form clusters, stars, galaxies, and so forth, and eventually form us. So in the theory of inflation, there was an exponential growth in the size of the universe at early phases, and all of the classical structure that we see in the universe was seeded by quantum fluctuations in the early universe. Now, there are a variety of different models that people construct which could explain this exponentially expanding phase. The most popular comes from what's called a scalar field. We studied the dynamics a bit of a scalar field earlier in this class, and the most popular models for inflation involve a scalar field, a conjectured scalar field known as the inflaton. Not much is known about the dynamics of the inflaton should it exist. It's very much a subject of current study, so I encourage you all to stay tuned. So perhaps I will conclude here. This finishes what I wanted to say about cosmology, so let me just see if there are any questions. So just an announcement. Let me remind you that we have class on Friday because Friday is a Monday. You have a problem set due tomorrow, and next class we will go onward and upward with our study of gravity waves. Okay, see you on Wednesday.